In this lesson, we will be looking at different properties of some exponential functions, and we will be graphing them and seeing some different things there. So, in this first one, I've asked you to graph y equals 3 to the x, and you may certainly use, in fact, I advise you to use your calculator to do this. If you need to make yourself a little t-table like this, and you plug in, you know, -2 for x and 0 for x and 4 for x, and go ahead and figure that out. You certainly may do that. I would probably suggest using your calculator and going to your table so that you don't have to do all of that work. So you're going to go to your y equals key, and you want to type in 3 to the x powers. So I will go 3. My exponent key is on the right hand side there, over x. And then I can go ahead and hit graph so that I can at least see sort of the general shape of it. So there's the general shape of it. And then what I want to do is I want to go to my table here. And my table is set kind of funny here. I'm going to start my table at -5 once. Hit graph. There we go. Okay. So, notice what's happening is if my x values are negative, and I will kind of go to my table here and check this out. If my x values are negative and I keep scrolling down, 7e to the -8, when x is -15, your y value is 7e to the -8. What that means is it's scientific notation for 7 times 10 to the -8th. So that's 0.000000 7 zeros and then 7. Okay, really, really close to 0. It's not exactly 0, but it's really close to 0. 2.3 times 10 to the -8th would be 0.00000023. Okay, very close to 0. On the other end, if I scroll up this way, my numbers you can see are getting bigger and bigger and bigger and bigger and bigger. And now they're starting to spit them out in scientific notation here too. So 1.1 times 10 to the 9th, 3.49 times 10 to the 9th. Your numbers get really big really fast, okay? So that's kind of what's happening. In order to graph this, you would want to have a few points to plot so that you can kind of see a little bit of a pattern anyways. So I'm going to plot the points -3 and 0.037. Okay, so I'm going to plot -3. Actually, I don't even have -3 on here. So let's go to -2 and then 0.037. So -2 and 0.111, and then -1 and 0.333. So -2 and 0.1 is just barely up there. -1 and 1/3 about. Okay, it's hard to get these on a graph, but, and then 0 and 1, 1 and 3. 0 and 1, 1 and 3, 2 and 9, 3 and 27 is where that would go. So you can see that it looks like this, okay? And as we looked, when we made x values really small, when we looked down here at this line, as our x values got smaller, this line right here got closer and closer and closer to 0. It never touches 0, it will never be 0, but it will get closer and closer and closer to 0. As this line moves up right here, it will get closer and closer and closer to infinity, okay? Obviously you can't reach infinity, but it's going to get bigger and bigger and bigger every time. Okay, so that's what's going to happen. All right, so your domain is what your x values can be. So think about, is there any number that you can't plug in as an exponent? You can plug in 0, you can plug in fractions, you can plug in square root symbols, you can plug in really big numbers, really small numbers. It does not matter. There is not a number that you can't plug in for your x values. And so your domain would be all real numbers. Okay? Your range is what your y values will be. Remember that this line that's down here will never reach 0 exactly. It will get closer and closer to 0, but it will never reach 0. And so your y values here have to be bigger than 0. They will continue to get bigger and bigger and bigger up here. So your y values have to be bigger than 0. Okay? In interval notation then, you're going from negative infinity to positive infinity for your domain, and your range is not including 0, so you need a parentheses at that 0, not a bracket. If it was including 0, you would want the bracket, but it doesn't ever get to exactly 0. And then, of course, it keeps your y values keep getting higher and higher and higher up to positive infinity. Okay? Your asymptote, again, is a line that it approaches but never touches. And it would approach this line right here, and I should have made it dotted, sorry. But that would be your asymptote in this case. And your asymptote would be the horizontal line y equals 0. All right, then this one, now I want you to go to your calculator and I want you to put in 0.25 to the x. So we will go back to our y1s and we will put in 0.25 to the x power. Go ahead and hit graph. Okay, this, oops, I got 3.25 in there somehow, sorry. Let's clear this out, maybe. 0.25 to the x power. Let's try that again. There we go. Okay. Notice the graph is going the other direction this time, which if you remember when we first started talking about exponential functions, if the base was bigger than 1, it will grow. And if the base is between 0 and 1, it will decay, like this one is doing. It's going down as I move to the right, so it is decaying. Okay? So again, I want you to be able to kind of plot some of these points from this table. So I'm going to go to my table and get some specific points to plot. This time, as we move, as our x's get smaller and I move that way, my numbers are getting bigger. At -4, it's 256. At -5, it's 1024. And it's getting bigger and bigger and bigger. It's going into scientific notation there. When x is -10, then my y value is 1.05 times 10 to the 6th. So that's 1.05, or sorry, 1050000. Okay, so lots. Okay. And then if we go the other direction, and we kind of scroll up. Now our numbers are getting smaller and smaller and smaller and smaller. 9.8 times 10 to the -4th is 0.00098. 2.4 is 0.00024. So they're getting smaller and smaller and closer to 0. Okay? But I want to be able to plot a couple of these points, and so I'm going to use this table to do that. So here we go. I am going to plot the point -2 and 16. And I will plot the point -1 and 4. -1 and 4. 0 and 1. 1 and 0.25. 2 and 0.0625. 1 and 0.25. 2 and 0.0625. And these numbers are going to get closer and closer and closer to 0 down here. So I will make the graph. I can connect my dots and it will look like this. Again, this line is going to get closer and closer and closer and closer to that x-axis, but never touch it. Okay? So, your domain, again, you can plug in any number you want for x. There is not a number that it won't reach. So, your x will be all real numbers. And then, of course, in interval notation, that means I would go from negative infinity to positive infinity. And then your range, again, you will never get y values that will be exactly 0 because that line will get closer and closer and closer to the x-axis, but it will never reach it. So your y values have to be bigger than 0 or go from 0 to positive infinity if you want to write it like that. And again, you will have an asymptote right here. This dotted line right here is your asymptote. It will never reach that line, and that asymptote, of course, will be at y equals 0. All right. In this case, this is a story problem. It talks about the pesticide DDT, which was widely used in the United States until it was banned in 1972. It is toxic to many animals and aquatic life, and it is suspected to cause cancer in humans. The half-life of DDT, and remember half-life means how long does it oh, it tells you about that in a minute. The half-life of DDT can be 15 or more years, so that's a really long time. Half-life is the amount of time it takes for half of the amount of the substance to decay or to be gone. So in this case, it takes 15 years for half of the DDT to be gone. Scientists and environmentalists worry about substances because they are hazardous and continue to be dangerous for many years after they are disposed. Okay, so this is kind of an example of what's happening with the pesticide DDT. And so it says after 60 years, estimate how many grams of DDT would remain. Okay, and so it says you have to be really, really careful, but it says along the x-axis that each interval is 15 years, and you have to be careful about this. So the x-axis, each interval is 15 years. So that means that this would be 0, okay? And then at 2, that means it's 2 increments of 15 years. So what that really means is that it's 30 years. And then 4 increments of 15 years really means that it's 60 years. Okay, so this is the magic spot here. I want to look after 16 years, but you have to be really careful to what's along the x-axis. If I look across here, it looks like it's maybe about 5 grams. Okay. All right. And then here we're talking about exponential growth and bacteria. Okay. So it says bacteria can multiply at an alarming rate. When bacteria splits into 2 new cells, then it doubles. For example, if we start with only 1 bacteria, which can double every hour, by the end of 1 day, we will have 16 million bacteria. So this says, after 14 hours, estimate the number of bacteria cells. Okay? So sometimes they will give you their graph like this. Okay? And along my x-axis, I will have the number of hours that are passed. So this would be 1 hour, 2 hours, 3 hours, 4 hours. Notice these are the two of the same graph, but scaled differently. Okay, this is the same exact graph, scaled differently. This is still 1 hour, 2 hours, 3 hours, 4 hours, 5 hours. Okay, so be careful, but this is scaled differently. Okay. So, I want to be careful when I do this. I want to, the y-axes are obviously scaled very differently too, okay? So, if you sort of look at what's happening here in your pattern, okay? So, it says, when there's 1 hour, there are 2 grams of bacteria, okay? At the end of 1 hour, there are 2 grams of bacteria. At the end of 2 hours, there are 4 grams of bacteria. At the end of 3 hours, there are 8 grams of bacteria. Notice what's happening. A pattern that you maybe will come up with is 2 to the 1, 2 to the 2, 2 to the 3. So basically when I'm doubling it every time, a shortcut to answering this without the graph, after 14 hours, estimate the number of bacteria, I could go 2 to the 14th power and get 16,384. Okay. I don't even see 14 hours on this graph right here. So this graph is not even going to really be able to help us. And I don't even know how the y-axis is scaled. Okay. So this graph right there is not really going to help us. I'm going to need to look at this graph. And I am assuming that on this graph, the y-axis tells me the number of bacteria. And this graph over here, the right graph, is the one that I will need to do in this case. Okay, if we use the graph to help us, 2 to the 14th algebraically is 16,384. If I use the graph to help us, hour 14 is right here, so I go up until I hit the graph, which is at this point right here. And then, of course, I look across. And if I were to estimate that myself just by looking at the graph, I probably would have said 16,500, which of course is close to the 16,384. So if you use the graph, you might get 16,500. If you use it algebraically, you can do the 2 to the 14th and get 16,384. Either one of those is okay because I am asking you to estimate. Okay, so as long as you're close or within reason, that is going to work.